Okay. Can you hear me well? Okay. So hi everyone. So I'm Doris Arzoumanian, and along with Rachel Friesen, we are going to provide an overview of our chapter where we try to follow the gas motion from bubbles and filaments to cores and disks. And so here on this, on this slide, you can see the list of authors that contributed to this chapter. And so we worked together to review recent observational and theoretical results to combine together and propose a comprehensive view of growth of structures in the interstellar medium leading to the formation of stars and planets. And so our picture of the star formation process can be summarized with this figure here, which shows, which highlights the various levels of interstellar structure spanning a wide range in, scales, from large scale 100 parsec scale bubbles down to parsec scale filaments and subparsec scale of cores and disks. So while these different levels of interstellar structure are interconnected and exchange matter and energy, they are all characterized by different 3D geometry, and different physical processes are dominate their evolution, which suggests that there is a partial decoupling between the different levels of interstellar structure, and it makes sense to identify them, analyze them, and discuss them as individual structures. So in the following, we'll provide some results that highlight the importance of and the link between these different structures of interstellar medium. So I will first describe the role of expanding bubbles in the formation of filamentary molecular clouds and the fragmentation of the filament into cores, and then Rachel will discuss the properties of cores, dense cores, and the link with disks. So there has been increasing evidence of the role of bubbles in the interstellar medium generated by expansion of supernova explosions that shapes the interstellar medium. So we have all seen this beautiful JWST image that shows the ISM dominated by bubbles. And then for me, this is very similar to what was proposed a few years ago from the theoretical side. And also yesterday, we heard the nice story of the local bubble by Juan. And here I show also a nice image which shows expanding two H1 shells shown here in red and blue, which interact with the molecular clouds shown in green. And so this expansion of bubbles, they compress molecular clouds into sheet-like structure where filaments form, and in particular, star-forming filaments form. So in the following, I will discuss the formation of the molecular filaments that leads to star formation. So here I show a few examples of numerical simulation studying the effect of expansion of large-scale bubbles on the ISM. So large-scale bubbles on the ISM, so on this plot here on the left-hand side, and then on the right-hand side, you can see a parsec scale, a smaller scale simulation, which shows very nicely how the propagating shock compresses initially roundish spherical clump into a compressed 2D sheet-like structure where filaments form. And so by combining different simulations of shock compressed layers with different magnetization and turbulent level, theoretical models for filament formation can be classified into 5 types, which are shown here. And I will go into details to explain the different types of filament formation within these shock compressed layers. So I will start from the right. So the first type is the type I, which corresponds to filament form at the intersection of 2 sheets. So this mode works only in highly supergalvanic and unmagnetized turbulent, and which is not very realistic with the observation suggesting of the ISM being in transalvanic turbulence. So the second type is the type S, which corresponds to filament forming through shear by expansion of overdensities through the turbulence, forming filaments that are parallel to the magnetic field. So this type of filaments, they have usually low line mass. They are like the H1 filaments, and they do not become star-forming. The next types are the type G and C, so where filaments are formed through the converging flow along the magnetic field within the sheet, and the filaments in this case is formed perpendicular to the magnetic field. So in the type G, the flow is induced by gravity, but this pure type G filament formation are possible only when there are no density fluctuation and turbulence is weak. And so in more realistic conditions, the flow is generated by turbulence. And so this is the type C for filament formation. And the last type is the type O, where O stands for oblique shock compression. And so in this mode of filament formation, the filament form at the converging flow of at the convergence of two flow in a band-like structure, where the flow in the curved sheet is generated by oblique shock compression. So to summarize, filament formation in this this model are in two-step process, where in the firstly compressed 2D gas layers are formed from shock compression, for example, induced by expanding H2 region, expanding large-scale bubbles, or maybe H2 regions also. And then within this shock compressed layer, 1D-like cylindrical filaments form due to the matter flow anisotropically within compressed sheet-like structure along magnetic field lines. And so Abe and collaborators, they did several simulations by varying the velocity of the shock compression, and they identified a critical velocity of about 5 kilometers per second that defines the type of filament formation. So when the velocity of the shock is smaller than this critical value, the type C dominates, so filaments are formed due to turbulence. When the velocity of the shock is larger than this critical value, the type O dominates, so oblique shock compression induces formation of filaments. And in this type O mode of filament formation, because the shock compression is high velocity, massive filaments are very quickly formed within a fraction of a million years. And this can be also seen in the filament line mass function derived from the simulation, where initially the filament line mass function has a steep slope, and then the filaments evolve in mass, so grow in mass by accreting surrounding material, and then the slope of the filament line mass function becomes shallower, and actually becomes, the slope becomes of the order of the salpeter slope of the IMF. And here I show the observed filament line mass function, which is very similar to what is observed in simulation, suggesting that maybe the filaments also form and grow as we just suggested. And so, as you can see on this filament line mass function, the small line mass filaments always dominate in mass and in number. And then the evolution of these filaments depend on the time scale of the shock. So once the shock attenuates, unbound filaments stop evolving and disappear through the turbulence. But once a filament is self-gravitating, it is long-lived and grow in mass by accreting surrounding matter. So to summarize, dense molecular filaments form through type O and type C mechanism, and then grow in mass through accretion and gravity-induced accretion. And gravity can also be important into collecting filaments that are formed separately into bundles. And this type of accretion onto self-gravitating filaments are suggested by transverse velocity gradients observed across self-gravitating filaments. So here I show a beautiful example of this from the observations. And this kind of transverse velocity gradient wouldn't be observed if the infall of matter or the accretion is isotropic from a cylindrical structure or a spherical structure, but could be observed only if the info is non-isotropic and within a sheet-like structure. And so this accretion is important in understanding the evolution of the filament. And here, so I will give some properties of filaments for from theoretical models of isolated filaments in hydrostatic equilibrium. And so these models, they say that when the line mass of a filament is of the order of a critical line mass of stability of these filaments, then these filaments are prone to gravitational fragmentation, and the spacing between the fragments is equal to 4 times the diameter. And when the filaments have a line mass which is larger than twice this critical value, which is of the order of 16 solar mass per parsec for 10K molecular cloud. So these supercritical filaments are expected to collapse without fragmenting, and their width is proportional to the thermal Jeans length. So if magnetic fields are included, this properties changes a little bit, but overall there is, as I will show in the next slide, there is discrepancy between what these theoretical models of isolated filaments suggest for the filament properties. So what do observations shows is that filaments that have line mass of the order of the critical value indeed fragment and form stars, but also observation shows filaments that have line mass as much larger than this critical value, which also fragment to form stars. So here you can see some examples of the observation. And the observations, the observed core spacing is not equal to 4 times the diameter, but it's more equal to the filament diameter, and which is also equal to the virial Jeans length. And also there are observational signature that there are 2 modes of fragmentation with a large-scale mode and small-scale fragmentation mode. And simulations showing filament accreting matter from the surrounding medium show that they can fragment and reproduce this observed spacing of cores, which suggests that these filaments are not isolated, but are in the interstellar medium and accreting and from it. And another important also result is that the filaments that are star forming, they have line masses which is close to the virial line mass. And by virial line mass, I mean effective virial line mass, taking into account kinetic, turbulent support and also magnetic support that are both important in order to support gravitational, support filaments against gravitational collapse. And the fact that this, so the observation shows, as you have heard earlier, that the velocity dispersion increases for high line mass filaments, which suggests that the virial line mass also increases with the line mass, suggesting that the internal turbulence can support these filaments against gravitational collapse. And the fact that these filaments are in virial balance is also important in order to understand another property of the filament, which is the inner width, which is observed to be of about 0.1 parsec, which is also of the order of the effective Jeans length. So while these filaments, they span a broad range in central column density and line mass, as you can see on this plot. And so these two quantities show a linear relation, and the proportionality between these two quantities is the width. So the fact that these two quantities show a linear relation suggests that the width doesn't vary much between these filaments. And here I show the distribution of the inner width of filaments observed in nearby regions where this, the Herschel resolution is 8 times better than the median width observed towards this filament, which suggests that this width is well resolved and gives an indication on the physical property of the filament. And the fact that these filaments have uniform width and the value is 0.1 parsec may have implication in our understanding of the colon density threshold for star formation. So here on this plot, I show the core formation efficiency, which is the mass within the core divided by the mass within the cloud at different colon densities in the cloud. And so since most of the cores form along filament, the background colon density of the cores corresponds to the colon density of the filament. And since there is this relation between the line mass and the colon density of the filament, then the colon density of the filament can be expressed in equivalent filament line mass, which is shown on the top x-axis. And so here on this plot, you can see that the core formation efficiency rises at the colon density of about 7 AV, which corresponds also to line mass of about 16 solar mass per parsec, which corresponds actually to the critical line mass of 0.1 parsec wide filaments. So this suggests that now we can understand the origin of the colon density threshold as being the colon density of filaments that are critically unstable and fragment to form cores. And another important also of the width of the filaments is that it gives a particular mass scale for fragmentation. So there are recent observations that show tentatively that the median core spacing, the median core mass observed along filaments increases as a function of the line mass of the filament. So higher core mass form along higher line mass filaments. And the median core mass formed along a given filament is of the order of the Jeans length, which is of the order of the line mass of the filaments multiplied by the width. So here I show two examples of core mass functions that pick at different line masses, different core masses for the filaments that have different line masses. And so now if we look at the full filament line mass, so the one that I showed earlier, we can see that the star-forming filaments are dominated by transcritical filaments, so filaments that have line masses close to 16 solar mass per parsec, and the Jeans mass of this Jeans mass of these filaments is of the order of 0.5 solar mass, which corresponds actually to the peak of the observed prestellar core mass function, which is shown here in blue, which suggests that the critical filaments are fragmenting into cores that corresponds to the peak of the core mass function. And also, so this on this filament line mass function, we can see that for the supercritical filaments, the filament line mass function shows a slope which is of the order of the salpeter slope of the IMF, which is also seen in the core mass function, which suggests that the core mass function is inherited from the filament line mass function, where higher mass cores form along higher line mass filaments. And so the CMF has been proposed as the origin of the IMF, and now with this observation, we suggest that the filament line mass function may be important in order to understand the origin of the CMF and consequently that of IMF. Okay, I will stop here, thank you, and Rachel will continue by giving some results on the dense cores properties.
Thank you, Doris. I am Rachel Friesen from the University of Toronto. So I'm going to talk now about the growth of structure and evolution of cores in molecular clouds. And so dense cores are the birthplaces of stars. And of course, they've been the topic of several previous Protostars and Planets reviews. So I refer you to those for some background. And I'm going to focus more on what's new since the last Protostars and Planets meeting. I'm also going to focus on low mass cores in particular, and with the caveat that I'm going to leave the fragmentation discussion to the talk after the chapter after lunch. And thank you to Marnouche and Kate for talking about magnetic fields, which I'm also not going to talk about in detail. I just wanted to highlight too, when we talk about starless cores, we're often defining our cores in terms of their star-forming properties. So protostellar cores are identified by the presence of infrared emission, or more recently by the detection of compact ALMA sources that might indicate there's a deeply embedded disk or young source there. And then the definition between starless and prestellar is generally focused on whether or not their mass is greater than 2 times the critical Bonner-Ebert mass, so discussing how likely they are to actually gravitationally collapse. So masses that are lower we define as starless, and then prestellar are those that have or core masses that are large enough that they should be possibly gravitationally unstable. So one of the big things that came up since the last Protostars and Planets, of course, is this knowledge that cores are, particularly these star-forming cores, are primarily found in filaments. And another, which is very important to understanding how they grow and evolve. And then also that we have many interferometers that can start probing the structure of these starless cores and protostellar cores on very small scales and multiple tracers. Another big change since the last Protostars and Planets is that we have these beautiful broad Herschel maps and other continuum maps from the JCMT that target nearby star-forming regions in exquisite detail. And now we also have a number of large-scale surveys that focus on molecular line emission to provide the kinematic counterpoint to those surveys across as much of a largest scale as we are able to do with the instruments we have. So I'm showing a list of a few different surveys that focus on nearby star-forming regions. There's also some posters that you can check out if you're interested. And here I'm showing you the Aquila region in column density of H2 from Herschel and reprocessed by Ayushi Singh. And in the white contours are the outlines of the survey area from the Green Bank ammonia survey in ammonia. And the dark contours highlight where we see the ammonia. So it highlights very well the high column density regions where the filaments and the cores are found. And these surveys cover a range of molecular line tracers, tracing lower or moderate density gas in the CO and other isotopologues through to higher density gas in ammonia and N2H+. So that, of course, like I said, gives you that kinematic counterpoint to the continuum surveys. So here is the same map, and now the color scale is showing you the line of sight velocity across this region. So this is Serpens South and W40, and you can see that the line of sight velocity actually doesn't vary a huge amount across the entire complex. Just a quick side note, and I'm not going to get into too much detail, but of course, the question of how you identify structures and where you draw the line has already come up this morning. There's definitely a number of different algorithms to identify cores in these observations, and of course, because they're embedded within filaments, how you define a core and how you subtract a background does matter in terms of understanding its properties. And so in observations, you're limited by what tracer you're using. Simulations have all the information, but then making that transition, how you identify cores in simulations versus in observations, you need to make sure you're comparing the same kinds of objects. So I refer you to the chapter for more discussion on that. So what do we learn from adding those kinematic properties to our data? And again, I'm going to focus on cores. There's a rich wealth of information you can learn from filaments, of course, once you add in the kinematic information. One thing we can do is aim to produce a more complete virial analysis of which cores are actually unstable or gravitationally bound or bound by other components. And what we're finding is that in many cores, when you factor in the kinetic energy and also the bounding pressure from the turbulent gas or perhaps the weight of the cloud, pressure actually dominates over the gravity. And so here we're showing that for a number of cores in nearby star-forming regions, the pressure term dominates both for cores that appear bound, but also for cores that appear unbound. In some nearby regions, work by Chen also identified these very compact cores that were very coherent, so their velocity dispersion is very low, close to the sonic level within the radius, but they're also very small, and so they're not gravitationally bound, but they're instead bound by the external pressure, and they fall along a line there that is lower mass but follows a similar trend in terms of the cores that we already observe. When we look at simulations, this idea that cores are not necessarily gravitationally bound, you can find this in various simulations. So if you have two-stage fragmentation, so fragmentation from filamentary structures, can produce cores that appear virally unbound at first, but then over time evolve to become, have lower virial parameters. And so you can also look at simulations and models where filaments and cores form dynamically and form simultaneously, and then you get a range of core properties that range from cores forming as pressure-bound objects, but also gravitationally bound as well, and then the evolution happens afterwards. And so one interesting study is this is work by Offner et al., where looking at cores, tracking cores in MHD simulations, and then using machine learning to categorize the cores based on their properties, found that you can actually separate some of these objects into different phases, where you have cores that are bound, which are the phase 3, cores that are coherent, which are the phase 2, and then turbulent dominated cores, which are phase 1. There's a couple interesting things about this, and I refer you to Stella's poster for more information. But first is that the evolution of these cores might not necessarily follow a simple trend where cores can actually go between these different stages. And in the case of cores that are quiescent or coherent, some of them end up as very long-lived objects and don't necessarily form stars. You can also try and map, based on the information we have, the observed cores onto the same kind of structure and see where they lie. And of course, the protostellar and prestellar cores do lie within this bound phase 3 selection, but then we have these other cores, which some of which may or may not form stars. Moving on to core dynamics, like I said, we have now a lot of observations that allow us to probe the internal dynamics of cores, from single dish to interferometer observations. If we look on the core scales and look at what our cores collapsing, 10 to 20% of starless cores show infall motions. And again, here the starless cores are starless and prestellar. They weren't making a distinction. And the infall motions are largely subsonic. But with just a core scale measurement, we really can't discuss too much different models of how cores might actually collapse under gravity. And so now with these high resolution observations, we can start looking at infall and rotation within cores. And really resolved kinematics are required to test these infall model predictions. And when we look at cores in small scales, we can see here that even though a core might show really what looks like a smooth velocity gradient consistent with rotation, when you look at the position velocity diagram, there's actually quite a bit of structure in the velocity, maybe multiple components. And so that's something that we can tease out now with higher resolution observations. And so here's another example here, looking at a young protostellar core, where if you try to match the velocity profile, you need to include modeling that includes both rotation and infall onto a very low mass source. When we look at the evolution of angular momentum, we have cores, and we've traditionally looked at velocity gradients across cores as indication, or at least we measure it as solid body rotation, measure a velocity gradient to interpret that in terms of its angular momentum. And so when we do that, here we've compiled a list of a number of surveys that have tried to measure the angular momentum, the specific angular momentum of cores as a function of core radius. And these core scale studies give a power law relation that's somewhere between solid body rotation and turbulence. So you're kind of in the middle. So turbulence is still playing a role in terms of the overall angular momentum of these cores, kind of on all the way down here on scales. When we look to resolve studies, looking at what's going on in the internal motions of these cores, there's been a few studies looking at protostellar cores to try and track that evolution of angular momentum down to predicted radius where it is predicted to flatten out and have constant angular momentum. And this transition point and how that angular momentum is reduced as you go to smaller and smaller scales is going to play a strong role in the size of disk that can actually be Keplerian and supported and rotating around a protostellar source. And so here there's just a few measurements, and we're starting to see, in some cases, we do find that there is an observed transition where you move to a constant angular momentum. In other cores, and this is work by Pineda et al., we go down to very small radii and don't see any indication of a turnover yet. So again, this is really kind of play a role. It's limiting where the class 0 protostellar disks are able to form and how big they can get. And velocity gradient measurements at somewhere around 1,000 AU present a range of actual specific angular momenta values, which kind of suggests that there might be a broad initial set of conditions for disks. Where is this angular momentum coming from? Kind of stepping back a little bit. So we've heard that if we have cores that are fragmenting from filaments, there's a paper showing that you can get the observed angular momentum, specific angular momentum dependence with mass if that angular momentum is inherited from the filament. You also have surveys or studies that show that you can get the same relation if it's inherited from the turbulent cloud, so showing that turbulent importance in terms of the angular momentum. And also anisotropic accretion from the environment, thank you, where the angular momentum, here is showing the angular momentum of the core, and then the angular momentum of episodic accretion onto the core from the surroundings. And what we find, or what the study finds, is that the angular momentum can be randomized and increased by quite a bit from accretion from that filamentary structures outside layers onto cores. So cores to accreting disks, most cores do not form and will not evolve in isolation. There's been recently a number of observations of streamers. So this is velocity coherent narrow structures funneling material around YSOs. And again, this would be a source of non-isotropic accretion onto disks. So we have accretion onto cores, perhaps accretion onto disks. It's been detected in multiple species. And this requires modeling to confirm. We have a very smooth, in the sources that we've detected, smooth velocity gradients and rotation. And they've been detected in a few different sources. And the infall rates of these streamers can be similar to the protostellar accretion rates. So it's a way of continually increasing the mass available to accrete onto the protostar. And we can see these around more evolved sources onto class 1 and class 2 sources. So this is a beautiful example of HL tau, where you also see not only this streamer that you see in the emission, but in Schock's emission from SO, highlights exactly where it seems that the streamer is landing on the disk. And in this case, at least, the streamer accretion, if that's what's happening, isn't actually impacting the structure of the disk. But of course, with only a few objects, we need to understand this in a little bit more detail. And so I want to highlight, this is a really popular topic. There's a number of posters here, so I expect to hear more about streamers at the next Protostars and Planets. We see asymmetric infall in simulations. So this, in varying MHD setups, we see this, these kinds of streamers. And the other thing that's interesting is that again, we're looking at connecting the scales. So extremers in some simulations seem to connect from large scales right down to the very small scale. So accretion onto cores, accretion onto disks, and it's all kind of seen like it might be connected. But of course, what we need to do now is, thank you, really use our data and increase the data that we have at really high resolution and sensitivity, and use our modeling to kind of compare predictions to understand how important this accretion is and how much of the mass is going to end up in the final protostar over time. So I just wanted to end with some open questions that kind of come out of the discussion in our chapter. So polarization surveys, thank you again to the hard work that's been done by all the magnetic fields people. Polarization surveys should allow critical tests of filament formation models. So, truly trying to understand what the predictions are and what we see. And similarly, the structure and orientation of magnetic fields within filaments and cores will affect core stability. So I didn't include that in the discussions. Thank you. And which cores are truly pre-stellar, and so how do cores evolve? How much of the mass that you end up with in a core comes from the outside to the inside? When we define a core, is that the mass that's really available for star formation? And then looking at where do we find the break in angular momentum? How well can we disentangle this complex kinematics? And how important are streamers to protostellar accretion? So just want to thank again our co-authors, and then Doris and I will be available for questions.
Okay, thank you so much. This chapter is open for questions, and please remember that we will have the conference photo just after this Q&A session. So please remain here. Okay. So, Ohashi-san.
Thank you. Nagayoshi Ohashi from AJA, Taiwan. So can you show the last slide again? Showing open questions.
This one?
Last slide. Showing open questions.
Oh, yes, sorry.
Yeah.
Sorry.
Yes, thank you. Yeah, I was just wondering, your fourth point, at which radius in a break in angular momentum in the protostellar course, which I'm very interested in as well. But what you're asking is that there might be some specific radius where we could expect to see the, a break, or, in some sense, such a radius could evolve based on evolution, like class 0 or early phase. The radius might be very small, but then later, the radius gets larger. So I just, want to get more comment on from you.
Yeah, no, thank you. I wasn't really saying that there should be an expected radius. Probably there are some models that predict where that radius is for various stages of evolution. But I think, what we're saying is that we've only been able to measure this, observationally for a few objects. And so, if we want to start investigating where that break is, we need some observational data. So I think my question is really more like, can we do this for more objects, in the next, 5 years?
Okay, thank you.
Okay, from back.
Thanks. This may be a question for Doris. Reward Spokerelli, University of Toledo. So if filament formation is hierarchical in nature and happening at all scales, as we saw in the previous talk, doesn't that automatically rule out this idea of a characteristic width of a filament of 0.1 parsec, which we mostly saw in nearby filaments only and observed with one kind of facility, especially Herschel? I don't know, what's your view on this idea of pushing this 0.1 parsec as some kind of universal thing? It's a characteristic of a filament or something like that. How about, we have learned that the filaments have different sub-filamentary structures also. Also farther away you have other kind of radius also. In one of the plot, the parabolic nature, there was a broad distribution. So I just wanted to see how you feel about that.
Yeah, okay. Thank you for your question. And so there are different aspects in your question.
Yeah.
First, regarding the importance of possible uniform width for filaments has implication in fragmentation of the filaments. So it's important in our understanding of the star formation process. And so it's important indeed to make sure that this observational result is robust and it's not affected by observational bias being maybe measurements or also angular resolution of the observation. So when we want to talk about the filament width, I think it's very important to make sure what kind of data we are using and what kind of analysis we are doing. And then the idea of the hierarchy of interstellar structures, I mean, that also depends on the angular resolution that you are observing. So if you talk about large scale, 100 parsec scale filaments at low resolution, if you go at high resolution, you will end up by seeing small scale structures. And so here what we are seeing in the observations is that at a given distance, at a given scale, we can measure a width which is about 0.1 parsec. And so coming back maybe to the relation between the filament width and the length, so which was shown by Rowan saying that there is a relation between these two. And actually, maybe, but on this plot, we can see that the filament length is much broader than the filament width. So if there is a slight tendency of having broader widths for larger filament, maybe that's an interesting aspect, and we have to understand if that's really the case. But on such a plot, we can see that actually there is a difference between the distribution of length of the filaments and distribution of the widths. And also, it's kind of understandable that if you look at in large-scale clouds, you would expect to see longer filaments, that when you look in smaller scale clouds, you can see smaller length filaments. And for example, this could be understood in this kind of filament formation process by shock compression. So for instance, if you look here you have a parsec scale clump that where filaments form. So the longest filaments that you can form in such a clump is like parsec scale length filaments. So if this clump is larger and then the shock compression forms other filaments in that larger scale, then you would expect to see larger scale filaments. So I think it's very important to make sure that at what scale we are looking and what kind of filaments we are discussing. Mixing inhomogeneous sample of measurements, I think it's not very interesting in order to discuss any physical processes, because inhomogeneous sample of filaments of structures can come from different physical processes, and mixing everything we cannot identify specific physical mechanisms.
Okay, thank you.
Okay, thank you.
Hi, thanks for the wonderful talk. I'm Yueh-Ning from Tata Institute of Fundamental Research, Mumbai. So I had a question regarding towards the end of the talk, you mentioned about the randomization of the angular momentum direction of the protostellar cores. So do you have any comments or thoughts on, like, what is the degree of randomization in any given cluster by these different streamers or different mechanisms? Are they completely randomized, or you still expect some bias?
So I'm not sure exactly what I would predict. Certainly the Kuznetsova paper predicted that overall the velocity gradient directions would end up being completely random. I would tell you to stay tuned. We are in the process of actually trying to correlate the orientations of cores, velocity gradients, magnetic fields across a large range of objects. So in general, I think we do see a lot of randomization. And you can see that in the orientation, in some cases, of outflows, which tell you about, presumably the orientation of the disks. In some filaments, they seem to be, perhaps aligned, but in other regions, they have tendencies to be more random. So I think we're seeing that, and we'll see more of that soon.
Okay. The back. Yichen Zhang from University of Virginia. So I have a question about the streamer. So I wonder if the create material, join the disk from streamer, and the streamer deliver material like as a rate as high as a creation rate. So would that like each such event significant change the angular momentum direction of the disk, or causing like a disk? How can the disk keep the same direction for a long time?
Yeah, that's a good question. I think something that, like I said, there's a number of papers or posters on streamers here, so it's a fairly new detection. Some of the accretion rates do seem to be similar to the protostellar accretion rates. Whether or not that's one event or a few events, or you have it over a longer time, would affect how much the angular momentum of the object has changed. So I think right now I can't say if there's only one event or multiple events that would have an impact on the overall variation in the angular momentum, but it's definitely something that needs to be thought about. Thanks.
Okay, so next from back.
Jongyu Kim from NAOJ. Thanks for the great talk. I have a question to Doris. So you mentioned these different types of filament formation mechanisms. And my question is, can these different mechanisms correspond to some different evolutionary stage of filaments? For example, this type O coming first, and then after that, gravity begins to dominate, and this type G type filament formation happens. And can we somehow observationally test, this kind of ideas?
Yes. So thank you for your question. Regarding the filament formation modes that will form self-gravitating filament and star-forming filament, so these are these types. So as I said, in order to the difference between type C and type O is on the shock velocity. So shock velocity, and so actually it's possible to disentangle these two types of filament formation from observations, because they have characteristic velocity structures. So here I have a slide on this. For the type O, filament formation, when the shock velocity is very strong, you form a bent sheet from which the flow forms the filament, and this kind of structure, this kind of formation mechanism expects velocity structure, which is shown by this V-shaped velocity structure on this position velocity diagram. And if the filaments are formed due to turbulence or gravity in the sheet, we expect to see this kind of velocity structures. So it's, I think, very interesting to check in the observations if we can quantify and see this difference velocity structure that would imply different modes of filament formation, and also can help to maybe constrain possible velocity of shock compression.
Thank you.
And so, yeah, in observations, there are some observations showing this kind of V-shaped velocity structures, and maybe some also tentative linear velocity gradients from this. But I think, yeah, it will be very interesting and important to try to do this statistically within a cloud to see which mechanism is more dominant, because as I said, the evolution of these filaments can be different depending on the shock compression velocity.
Thank you.
Mordecai Maklo, AMNH. I this is kind of a follow-up question now, which is, why do we need the shock front to form a filament if gravity naturally forms sheets whose intersections are filamentary? Could we have a purely gravitational structure? Sure, it can be influenced by shocks that are around, but gravity alone is perfectly effective at forming filaments, isn't it? I don't know which of you wants to answer this, since Kate actually put up a future question, maybe her, but.
So for example, in this simulation here, let me see here. So in this simulation here, we have filament formation in a run where there is no gravity. So which means that these filaments form without gravity. And then gravity is important for the evolution and the accretion of the filaments. And the idea of the importance of the formation of filaments in sheet-like structure is because in the observation we see very commonly these velocity gradients across the filaments. And as I said, those velocity gradients, you cannot see them if you are not in a sheet-like configuration. And so, and also the fact that we see bubbles everywhere, and so the bubbles compress molecular clouds forming sheet-like structure. This suggests that the formation of filaments in sheet-like structure maybe is a very widely spread mechanism. And regarding gravity, so if there are no density perturbation, the density inhomogeneity, you would expect to form filaments through gravity. But because you have density and velocity perturbation, gravity, formation of filaments through gravity takes longer. And so what is faster is the formation through turbulence. So in this kind of simulation, if you wait longer, then you will have formation of gravity, formation of filaments through gravity, while you have formation of filaments through the other modes that is faster.
Thank you. Okay, thank you. So it's running out of time, but actually this is one final question. Maybe he is lining longer. Okay, so.
So thank you very much. So Shota Notes from University of Tokyo. So my question is about the streamers, but different direction. So recently the observation detected several molecules across the streamers. So from theoretical point of view, is there any typical temperature of the streamers? So the streamer is cold or warm? Would you please make a comment on them?
That's a good question. I mean, I would expect, if the streamers are coming, in these, low mass cores, overall the low mass cores are cold, the protostar isn't going to heat the gas, significantly beyond, a very close region. So I would expect the streamers would be cold as well, and that makes sense given that we're detecting them in these cold gas, dense gas tracers. But I haven't thought about the theoretical predictions.
Okay, thanks.
Okay, thank you. So let's thank the both speakers again.